So with that, I'll introduce our speakers. Dr. David Jones is Associate Director of the University of California Research Center in Davis, California, where he manages the research into sustainable road and airfield design with special interest in pavement recycling and use of recycled materials in pavement layers, low-volume road management, and permeable pavements. So he's working closely with the federal, state, and local agencies to implement research findings, evaluate performance, and refine the life cycle costs and life cycle environmental impacts and various initiatives. And I guess I would add to that, David Jones is a wonderful man, and you'll enjoy hearing him speak today. He's talking a little bit about the interlocking pavements, mechanistic designs of permeable pavements based on accelerated pavement testing, interlocking pavements, but he'll be talking about kind of the design that needs to be basically the bathtub, or down in Southern California they call a swimming pool, that's under the road to collect that water and let that flow into the earth. So that's how these kind of work out. He's been working heavily with David R. Smith, and let me give a little intro on him. But he's the real reason that they got to do this type of testing out there at their facility at UC Davis. Since 1977, David Smith's been working with civil engineers and contractors in design and construction and maintenance of permeable pavements, so he's got a lot of experience there. He's been working on technical bolt-ins for permeable interlocking concrete pavements, PICP, a new terminology for me in that way. But he's co-authored many manuals and different courses on the topic, and has taught classes on this whole topic in itself in many states. He's also been working with ASC related to permeable pavements, some that's been released in 2015. He's been helping guide guidebooks since 2000. His latest book is the 5th edition of the Permeable Interlocking Concrete Pavements, released in 2017. And he's also working on some ASCE Art 6818 that's been released in October. So he's got a lot of experience related to pervious pavements. And he's been working with David Jones to do some of the stuff that he'll be covering in this presentation today. So again, this David will go into kind of the background of the facility and also how this all came about for this study. So again, David, if you'd please take it from here, and thank you.
Okay, thanks Ben for the introduction. And morning, ladies and gentlemen. Thanks for coming along and giving us the opportunity to share this research with you. I would certainly like to acknowledge David Smith. It was wonderful working with him, and on this whole project. It was a real fun event, and we learned a lot, and it just all worked well in the end. Also like to acknowledge the co-authors here. Wei Li and Rongzong Wu did most of the work on the mechanistic design, so I'm not going to take any real credit for that. And then obviously John Harvey, who sort of cast an eye over all the events and gave us some technical guidance there. So the presentation today is on the full-scale structural testing and development of design guidelines for permeable interlocking concrete pavement. I think just an interesting concept, and certainly another thing to look at in terms of managing stormwater. So outline on the presentation today, a little bit of an introduction. We'll go into the test track design. Talk a little bit about the test track construction, so you can see the swimming pool effect that Ben mentioned. We'll talk about the accelerated load testing, just what that involved. Quick look at the key test results that came out of the study. Take a look at the design procedure that we developed from those results, and then go to the summary and the wrap up. And then I'm going to hand over the mic to Dave Smith, and he will add some information about where this has all gone. Our deliverable to Dave was a final report along with a design tool to design these pavements, and then basically Dave packaged that in various forms, and he'll share that information with you. All right, so when we started this study way back, we did started doing some work for California Department of Transportation. There was a lot of interest in using permeable pavements in higher traffic applications. So typically, they were out there being used on car parks, golf cart tracks, that sort of thing, but nothing really carrying a lot of heavy traffic. And the idea was that, you know, could we use these in instances where we were putting some lighter highway traffic on there, and using it for you know, truck alleys, that sort of thing in towns where there were stormwater problems, and getting the water into the subgrade as opposed to trying to pump it out some other way in some other drainage system. Certainly a lot of interest in doing that. So that kind of drove the study. We had done some earlier work for Caltrans between 2008 and 2010, but it was pretty much a desktop study. We looked at trying to do some basic mechanistic design, and looking at ways of improving the strength and the stiffness of the underlying layers so that we could put more heavy vehicles on it, and just even more car traffic, but higher volumes. And that kind of culminated in some recommendations to do some real live trafficking. We looked at ideas of using it as like retrofitted shoulders on highways, and even on some of the, you know, lower volume Caltrans roads to actually where there were problems with drainage, to potentially look in that area. But that study didn't move much beyond that desktop study, and we never had the opportunity to do validation with traffic. So it was at that time that we got to talk with David Smith, and he was very interested in taking it further. And he basically came up with the money to build a test track, and test it with interlocking concrete pavers, or the PICP, the permeable interlocking concrete pavement. So although the Caltrans study was focused more on HMA and pervious concrete surfacings, the idea obviously from David Smith's side was to look at using the pavers on the surface, but the fundamentals of doing the actual pavement design, which is focused primarily on the thickness of that reservoir layer, that layer that's going to be storing the water during these high rainfall events, is basically the same whether you would be using a interlocking concrete paver or a asphalt or pervious concrete on the top there. So the fundamentals can be carried across. So ultimately, the objective that we were set for this whole study was to develop a mechanistic-based design tables for permeable interlocking concrete pavements. So the study approach, kind of, you know, standard study that anybody would do, was started off with a literature review to find out what work had already been done on the higher traffic pavements. Interestingly enough, out of that whole literature review exercise was that a lot of the research at that time had really been done on managing the water flows, not so much about the actual trafficking. So there was less information on that, and certainly not a lot of information on the heavy duty pavements, apart from some work that had been done on ports. We did some field testing on some existing pavements in Northern California, to get a basic idea of what kind of stiffness we could get out of these. We did not use FWD because there had been an earlier ARRA study that had looked at that, and I think, you know, just because it's a very disjointed pavement, very difficult to get anything meaningful out of an FWD. So we used what we call an electronic Benkelman beam. It's just a modified Benkelman beam, and we positioned the feet so that every one of those was actually on a paver and not on a joint. And we got some pretty useful information out of that. So using that, plus some basic laboratory testing results that we had from the initial study, we came up with a test track design using the approach that we had developed for Caltrans. Then went on to the test track construction, which was overseen by David Smith. Once the track was constructed, we did the accelerated wheel load testing, analyzed all of those results, developed the design tool, used the design tool to develop the tables, and then put together a final report. And as I said, that's gone further in terms of how David Smith and his group has used that information, and as I said, he'll discuss that a little later on. So the final report that we developed, that is on our website. This is our website address down the bottom here, so you can download that from the website if you want to read through all that data. Moving on to the test track design. We designed it for unbound layer rutting. If you take a look at the photographs on the right-hand side there, cracking is not really an issue because this pavement is about as cracked as it could be before you even start. So, basically the whole focus was on the unbound layer rutting. The approach that we used to try and work out those thicknesses was based on some earlier work that was done by Marshall Thompson on airfield design using the shear strength to shear stress ratio at the top of the layer. And we kind of worked with the range that had been developed from various studies at Illinois, looking at 0.3 to 0.7, somewhere in that range. So anything below 0.3 or less than 0.3 would make a very strong pavement and potentially stronger than you would need. Anything more than 0.7 is pushing towards the weaker side, and you're likely to get subgrade rutting or rutting in that specific layer. Required inputs for that was the unbound layer stiffness, which we basically got from our Benkelman beam measurements out on the pavements, plus a little bit of triaxial testing information that was out there. Strength of the materials, essentially from laboratory testing. Cohesion, friction, that sort of thing, also from lab tests that we had done, as well as some work that had been done at up in Illinois as well. So got a lot of data there that we could play around with. So the design of the pavement, the sort of top layers were basically standard because that's essentially what is general practice and based on empirical experience. This is what works. So the surface was a 3.5-inch interlocking concrete paver. The bedding layer, which is what the pavers sit on, was 2 inches of ASTM number 8 aggregate. Also, permeable, obviously, but very fine. The base layer underneath that was 4 inches of ASTM number 57 aggregate, and this basically forms an interface between the very fine sandy material, which is your bedding layer, and the very coarse aggregate, which is your reservoir layer. The reservoir layers, we had 3 varying thicknesses because we wanted to look at a range of different thicknesses to see how they were affected. And that was made out of ASTM number 2 aggregate, so kind of looks a lot like railway ballast. There's a photograph of it on the right of your screen there, and if you take a look at that, there was quite a variation in grading in terms of from the smaller sizes to the larger sizes. And there was a lot of the aggregate had elongation properties on that. So David Smith sourced this material. He basically looked at various quarries in the area, came up with this. This was very strong aggregate. It had a very high Los Angeles abrasion resistance, so good strong material, but a little flaky in terms of that elongation. And then the subgrade soil was basically what was there. It's a silty clay, compacted, that was compacted after the excavation, but no other preparation, certainly no stabilization in the subgrade. So basically the whole design, everything else was fixed. The only variable that we were playing with for the study was the subbase layer thickness. This is kind of what we came up with. So 3 different thicknesses, a thin, a medium, and a thick. Remembering that shear stress to shear strength ratio of 0.3 to 0.7. So we went a little higher because we wanted it to fail to see what it looked like when it did fail. And in terms of the stronger one, we just went a little thicker than normal, just so that we had a control that we didn't think would fail, and then obviously one in the middle of the range. So we ran our numbers, and we came up with some pretty thick pavements, which was telling us that our original designs were probably going to be overly conservative. So we dumbed those down a little bit just to make it constructible and affordable. So on our thin pavement, we went at 18 inches or 450 millimeters. On our medium thickness pavement, we went with a thickness of 26 inches. And then on the conservative one, we went at 37 inches or 950 millimeters. So 3 different thicknesses of the subbase or reservoir layer. All of the other layers were a fixed thickness. So I'm not sure if you're going to be able to see this, but this is a top section of it. So basically, we built all 3 thicknesses in one track, so we could test them all together with a single pass of the heavy simulator wheel. This is the thin section here, and you can just see the different thicknesses of the reservoir layer. The other 3 layers, all of a fixed thickness. Moving on to the construction. So this is our facility in Davis, California. If you don't know where Davis is, it's about 60 miles northeast of San Francisco, up in the Central Valley. This photograph was taken during one of our drought sessions in the summer, so looking a little dry. So this on the left-hand side here is our track for the pavers. The other tracks are just ongoing asphalt tracks that are being tested here. So this is a track here that was being tested for warm mix asphalt, I believe, at the time. The outside track was being tested for some open graded friction courses. But this is the track that we're talking about here on the left-hand side in the circle. So this is the start of the excavation. So it was basically undisturbed land that we had done it. Prior to us moving onto the site, it was basically an alfalfa field, so it looked like what the road looks like on the back side of the picture here. That's basically what the land had been used for before we had turned it into a permeable pavement. So this was the start of the excavation. That was what it looked like at the end of it, hence our swimming pool rather than a bathtub. So this is the deep end, this is the shallow end, this is the middle section here. So after we had excavated it, they just put a roller in and we just rolled it, no other further excavation. So we didn't rip it up and then recompact it. It was just basically a light compaction on that surface. That was followed by the installation of a textile. This was primarily just to prevent pumping of the fines from the surface back into the layer and preventing that reservoir layer from clogging, but obviously would still allow the water to flow through. Then the reservoir layer was brought in. These orange pylons here are where our instruments were for measuring the deformation in the underlying layers. I'll get to that in the next presentation. But this was basically put in, was compacted with a roller as we were going in, and then also a plate compactor just to give it some final orientation. The base layer on top of that, then the sand layer on the top of that, and then the pavers going in. So all done mechanically, typically as it would be constructed if it was a real live project. And again, you can see the instruments still sticking out here. This over here was a moisture sensor, so we could determine where the water level was in the subbase layer. And that was the final product. So, good construction. We were happy with it. To say we were only observing, not advising. David Smith basically was here to oversee the whole process, had a great contractor to work with, and we were all very happy with the consistency of the track and what we got out of it at the end of the day. In terms of instrumentation, our standard instrumentation that we would typically use on an accelerated test was kind of difficult because of this really big chunky aggregate. You can't really stick anything to this, so your conventional strain gauges, pressure cells, those sorts of things, basically you can't use any of those kind of instruments on this particular material. Same thing with our multi-depth deflectometers to look at deformation at various levels. Again, we just could not use that in here because we had nothing to stick the LVDTs to and give us a representative reading. So basically we went with pressure cells, but we only put those on top of the subgrade and the top of the base. So that was the intermediate material on top of that reservoir layer. That gave us some indication of how the stresses were being distributed at the various levels. We then developed our own instrument. Basically was just to look at measuring deformation in the different levels. It was a pretty simple device. You can see it on the top right-hand side of the screen there. And these were just tubes with a metal base that we installed at various levels in the pavement, and we could actually measure the movement of this whole instrument against a reference on the surface. And we just dropped a dipstick down these holes, actually drilled a hole in the concrete paver, which fitted over the top of this, which then allowed us to take those measurements. And we had those measurements placed on the top of the surface, on the top of the base, and the top of the subgrade. So we had a good indication of where the deformation was happening. Again, we measured the deflection with the road surface deflectometer, which is essentially just a modified Benkelman beam. And then we monitored water levels both manually with dipsticks, and we also had an automated sensor system that measured where the water level was as well. So when we were doing the wet testing, we could control where that water was. Moving on to the accelerated load testing, we tested with an extended heavy vehicle simulator, so that allowed us a 13-meter long test track that allowed us to test the whole test track in one single pass of the heavy vehicle simulator, so we could do a direct comparison. A little more simpler than if we had built 3 separate test sections and tested them independently. Would have been very difficult to control in terms of the moisture content. So we chose that, going with shorter sections, but with being able to test all at one time. We used a bi-directional trafficking with Wanda. So we had the HVS running in both directions. That speeded up the process. We didn't think there would be any problems in terms of healing or anything like that on top of the concrete blocks. And then we used a wheel load range. Sorry, this is in metric. But ranging from 25 kilonewtons, which is about half a standard axle load, going right up to 80 kilonewtons, which is twice a standard axle load applied with that single wheel. And then we tested in 3 different conditions. So we had 3 different test sections within that test pavement. We tested the first one dry. We tested the second one wet. And for us, wet was defined as maintaining the water table at the top of the reservoir layer. So that pavement was essentially flooded. And we just kept the water. We just kept topping up the water so that the water level was always at the top of that subbase layer. Then we allowed the water to drain out. So we had no water in the reservoir layer, but the subgrade was wet, and then we ran another test on that. So we basically went from perfect conditions with no water in it, so we expected little problems with that. We then went to worst case scenario with the pavement full of water all of the time while we were testing, and then we went to a more realistic scenario where you might have a little bit of water, but that would drain out pretty quickly. And then all testing was done at ambient temperature. We did not try to control it in any way. And then the failure criteria was set at an inch of surface rut, a little higher than you would typically use for an asphalt pavement or a normal concrete pavement. But bearing in mind is that if the permeable pavement is working well, you won't have any water retention on the surface, so you technically wouldn't have an aquaplaning problem along those lines. So we went a little deeper with the failure criteria. So that's a shot of the extended HVS. So basically the standard HVS has an 8-meter test track. This one had a 13. We just basically bolt a center section into the middle of the HVS, and then that's basically just a shot of the wheel, not actually on the permeable pavements, but what the wheel looks like with a super single tire going backwards and forwards there. And then that's a shot of when we had finished the dry test and starting the wet test. So basically we flooded the whole test track right up to the surface, and then we allowed the water to drain back down to the top of the subbase layer, and then we maintained it at that area. So full of water before we actually started the testing. If we take a snapshot of the results, obviously you don't have time to go through that. We collected a humongous amount of data, but just looking at the basic rutting. So this is a visual photographs of the 3 different sections. So on the left-hand side of your screen, we have the dry section. You can see there's a little bit of a rut underneath the straight edge there, and this is the view from the shallow end. So the deep end is at the far end of the photograph here. This is the shallow end with that 450 millimeter thick reservoir layer. This is the same track after the wet test, so you can see a significantly deeper rut on the surface here. And then the section over here is the one with the drain subgrade, with the drain subbase, but the wet subgrade, and that performed very similar to the dry test. Interestingly here, so even though we had a very deep rut, we went beyond the 1 inch on the thin section in order to get 1 inch on the thicker section. You can see none of the pavers were pulled out. They certainly moved here on the edge of the section, but nothing pulled out, and none of the pavers broke. So even the ones that had the hole drilled through it to allow us to do our measurements, there was not one block that cracked on that surface. This is the total rut that we measured on all 3 sections. So the left-hand one is the dry test. This is the wet test. The black line is the thin section. The red line is the intermediate section, and the blue line is the thicker section. So kind of as you would see it. These vertical mauve lines, that's the loading. So we did the first part of the load at about 3/4 of a standard axle load, or 25 kilonewtons. Remember, this is a single wheel load, so you have to double it for an axle. This line up here is where we tested it at the standard 8.2 ton axle load of 40 kilonewtons, and then the 60 kilonewtons is 1.5 times an axle load. And then over here in the wet test, we ran it even higher just to see what would happen. So we went twice the standard axle load on that one. So this one was heavily overloaded. So on the dry test, you can basically see, kind of as we would expect it, the thin section had the highest deformation, total rut measured on the surface. The thicker section had the least. And you can see basically on that thin section, we ran it until we had the 1 inch of surface rut. You can see a major difference in the wet test. The y-axis scales are the same. So with the less than standard axle load, not too bad. But as soon as we went to the standard axle load, we started getting heavier. Again, we stopped at that 1 inch, but with the testing, but then carried on to see what would happen if we overloaded. So a significant difference when we overloaded. We have some major problems with that total rut. And you can see that the thinner section definitely rutted at a faster rate than the thicker section. So this was the optimal design. We think this one was a very conservative design. Moving on to, I'll show you just the thin sections and where the actual rutting was. I'll show you the thin section and the thick section. So the distance between the red line and the black line here is the rutting in the subgrade. The thickness, the rutting here between the red line and the blue line is the rutting in the actual reservoir layer itself. So that's in that railway ballast material. And then the gap here between the blue line and the top of the plot is the deformation that was in the bedding layer and that base layer. So you can see a little bit of early settlement densification underneath the wheel load. Again, we're going to a pretty heavily loaded axle right from the very start, but that remained constant. It didn't change much. The reservoir layer itself, that was a bit of a surprise that we got so much rutting in that reservoir layer. So again, pretty early settlement and then pretty consistent. But then when we went to the overload phase, we got a little bit more of it. and then you can see quite a lot of deformation in the subgrade layer itself, around about 10 millimeters in that subgrade layer itself. When we went to the wet testing, big difference. Obviously, again, those y-axis scales are the same. So some early settling in, but the subgrade rutting, which we obviously want to prevent, that kind of went down. And as soon as we went on to the heavier loads, some pretty serious damage in the subgrade. So again, distance between the red line and the black line is your rutting in the subgrade. Between the blue and the red is the rutting in the reservoir layer, and the top of the plot to the blue is the rutting in that in those surface layers. So again, that remained fairly constant, but a lot of rutting in that layer. And we put that down essentially to that elongation of that material and essentially just reorientation of the particles. Because they were wet, they were lubricated, reorientation of those particles, which gave us that densification. So that can probably be overcome by better material selection, making sure we've got a more cubical type of aggregate rather than the elongated aggregate, potentially to do some better compaction in that heavier roller, perhaps more vibration, to make sure we get that orientation before the traffic gets onto it. Next slide. So this is the very thick one. I'll skip the intermediate because of the time that we have, but this is the conservative one. So you can see basically in the dry test, almost no rutting in the subgrade at all. A little bit of reorientation of the aggregates here. So at one time we were getting a little bit more rutting in the reservoir layer than in the subgrade, but at the end of the day that kind of evened out. And then when we went with the wet, we only had a couple of millimeters of rutting in the subgrade, which is essentially what we were looking to do. Some of that could have just been punching of aggregate into the and reorientation of that aggregate into the subgrade. But again, you can see most of that rutting that happened on this section was actually in that reservoir layer. So the same problem, regardless of the thickness of that reservoir layer, we still got some rutting in there because of reorientation of those larger aggregates. So just some general observations. Obviously a significant difference between the wet and the dry testing. The wet test rutting was in both that reservoir layer or the subbase and the subgrade. So the take-home message from that was that even though we made that layer a whole lot thicker, it didn't actually necessarily prevent the rutting in the subgrade. So we have to take into that consideration, if we're designing these pavements, we're building those pavements, we have to take that aggregate selection and the construction seriously when we build those layers. The subbase aggregate properties and the construction quality, as I say, are critical to minimize that rutting. So moving on to the design procedure, taking all of that information that we collected from that and turning it into something that we could use for the design procedure. So obviously that initial test desktop study that we had done for Caltrans was very conservative. So we basically reworked those models that we had to come up with something that was a little bit more representative of the test track. We developed rut models for each of the layers in a typical pavement design that we had out there. So including those surface layers, the intermediate layers, and then the rutting in that subbase layer and the rutting in the underlying layer. We basically then validated those rut models with our APT data, and then ran an analysis in terms of getting the stresses and the strains under the wheel using the Open Paveware software package that was developed by one of our guys here. We then incorporated all of that into a simple design tool based in an Excel spreadsheet, and basically the input parameters into that are the number of days with water in the subbase. So you basically design it on the number of days that you expect there to be water in that subbase layer. So depending on, if you're down in Florida where you might have some very high intensity storms where you might have water in there for quite a while during the wet summer months, versus say Arizona or something like that when you're probably not going to have very much water in the layers at all. Some basic material property inputs, so you can actually put real numbers in there, or we have 4 different scenarios of materials going from a marginal material to a very good material. and then to put in your traffic and load spectra. Again, there are default values in that in the tool, but if you want to put your own real data in there, then you can do that as well. And then we ran the tool to validate what was the existing ICPI, the Interlocking Concrete Pavement Institute design tables that were essentially empirically developed. We then used the tool to validate those design tables and adjust them where necessary. And what we found was that the design tool was basically coming in at a little less conservative, so designing thinner pavements on the much drier or the drier ranges of materials, but a little bit more conservative, so slightly thicker under very wet conditions. And we also went a little bit beyond those original ICPI design tables, right up to, I think, about 130 or 150 days of water in the continuous water in the in that subbase layer. So again, you probably won't be able to see this on your screen. I can hardly see it on mine. Basically the design tool. So these are your input parameters here. In terms of your thickness, your subbase layer, your subgrade clay, some basic properties: thickness, stiffness, Poisson's ratio, cohesion, friction angle. This is all of your traffic information. As I said, there's a lot of there's all default information in here, but you can put your own in. Whoops, sorry, back again. And then this is basically your output information. This is going to tell you your rut depth for the given traffic and your given design period. And then you can also put in here what your allowable rut is, and then it's just going to tell you, yep, it's satisfactory or it's not. So pretty simple tool. I think it's pretty stable, and Dave Smith and his folks have been able to use this to take it further in terms of developing design tables. We ran some design tables of our own. We gave actual options, and these are included in the report. We gave actual options of a fixed number of days, or we also went with the range. So we have 0 days, less than 10, 11 to 30, 31 to 50, and this goes right up to about 150 days of water. Again, from marginal properties in terms of your stiffness of your materials under dry and wet conditions, up to and your cohesion and your friction angle, right up to good properties. So we have marginal materials, 2 intermediates, and a good material in there. And then based on your traffic volume, we go right up to 1 million easels, because we actually ran our wet test up to 1 million easels with the overload. These numbers here would then basically be your thickness. So you choose your material properties, and then you would have your thickness of your layer. So pretty simple tool that came out of it at the end of the day. So just to wrap it up, I think using that shear strength to shear stress ratio approach was very appropriate for permeable pavements. It's based on an airfield design where you have a high traffic load on the top and potentially marginal subgrades at the bottom that could be under wet conditions. You don't want to have any problems in that subgrade. So a great approach to use for that. A key thing was that the subgrade rutting was dependent on that subbase thickness, not necessarily dependent on that subbase thickness, and that you would have to design for wet conditions. That subbase thickness did not prevent the subbase rutting necessarily. Certainly dependent on those aggregate properties, so potentially a more cubical aggregate, and obviously your construction quality, making sure that you had good compaction in those aggregates. We did do some basic runs with the design tool to look at potentially putting a pervious concrete subbase below that reservoir layer, so that you would have a good platform to compact on and a nice stiff layer at the bottom, but still being permeable. And if that cracked, it wouldn't be a problem, because that would just be your permeability, but you would still have a platform to work on. That did allow significant reductions in the thickness of that subbase layer. So going for those higher traffic volumes, the thickness of that subbase layer was being dictated more by traffic than by water. if you put a pervious concrete layer below that, then you were pretty much designing more for the water than for the traffic loading. So we did not test that under traffic. I want to emphasize that we did not test that under traffic, but we ran the models with theoretical thicknesses and stiffnesses, and that certainly showed that we could reduce the thickness of the pavement. And then obviously the outcome of that was a mechanistic design tool, so you can put real data into that, or you can use default data, and then that whole tool was used to come up with revised design catalog that ICPI was then able to take further in terms of permeable pavement design. So that's all I'm going to say. So Dave, if you're there and if you're muted, you'll be wanting to unmute yourself. I'll give you the next slide, and you can take it from there.
Okay, very good. Can you hear me?
Yes, I can.
Okay, and everybody else? Okay.
Yeah, we got you, Dave.
Sounds good. David, thank you for that great presentation. Yeah, I just want to indicate where things have gone since this research, which was done in 2013, 2014. There's two publications that have come forth from it, and the one on the left was just recently published by the American Society of Civil Engineers. This particular document was about 4 years in the making, and it is a ASCE ANSI standard on permeable interlocking concrete pavement. It's about 90 pages. You can purchase it from ASCE, and it does include a summary of the UC Davis work, and then more importantly, it includes the structural design tables and method that's based on the number of wet days per year, depending, of course, on the location. It explains how to calculate the wet days per year, which is essentially looking up. You can do this on the NOAA website. You can look up the number of days per year the rainfall depth exceeds the 24-hour infiltration rate or depth of the soil subgrade, and you match that against the table, and then as David indicated on the tables, find the appropriate soil subgrade characteristics, and then your easels, and then come up with a subbase thickness. So that method is explained in the ASCE, as well as hydrologic analysis as well. Now, the publication on the right is my latest tome. It's the 5th edition of our design manual, published by the Interlocking Concrete Pavement Institute on permeable interlocking concrete pavement. I've been writing this book since 2000. It's the 5th edition. It's only taken me about 5 tries to get it right. So this particular book is about 110 pages or so, and it does include the UC Davis design method. It includes the tables as well, but it includes a lot more information on construction, on specifications, on maintenance, actually, as does the ASCE publication on the left. So that book can be purchased from ICPI. If you're interested in receiving a free copy, just drop me an email with your postal address. I'll pop one in the mail. We prefer to send out printed copies. They tend to not be forgotten. So the other item in both of these documents that we included since the tests in 2014 is we included lightweight deflectometer testing and acceptance criteria for the base layer. I think it's no deflections greater than 0.5 millimeter. We have since done some other work around the country testing open graded bases and have arrived at least a working number for quality control, quality assurance, acceptance deflection of LWDs. I thought the folks from Minnesota DOT would be interested in that, because Minnesota DOT is one of the leaders in using LWDs in construction of road bases, as well as compaction of subgrades, soil subgrades. So the next slide, if you would, David, just one more. Okay. Another thing we've done is, and this is just we're almost done with this project. Some years ago, Applied Research Associates, aka Dave Hines, developed Permeable Design Pro software, which includes hydrologic analysis. We kind of borrowed the algorithms from FHWA's drainage requirements and pavements, their drip calcs, and put them in there. And we originally included AASHTO 1993, and that's kind of what we were comparing against. We had the 1993, we had tables using the AASHTO 93 guide, and we kind of downgraded the layer coefficients for the open graded materials. But I developed tables, published those in 2011, and that's when, later on, 2013, is when I approached UC Davis on, hey, these tables are theoretical, we need some real validation here. And so they came up with the research and, of course, the design method and the tables based on the number of days per year water stands in the subbase. So what we're in the process of doing now, in fact, I just looked at a beta copy, is we have folded the tool, it's sort of a form of OpenPave. We basically have folded in the cohesion and internal friction angles into this software so that the design tables, as well as the number of wet days per year, for a whole ton of locations in the US and Canada, we folded that into this switch and systematically the design data, and then come up with a subbase reservoir layer, depending on what the hydrologic requirements are, the runoff and contributing drainage area runoff, and compare that thickness to the structural design using the UC Davis method. And of course, pick the thicker of the two subbases. So that's essentially how it works. It also has a CAD output. If you're interested in receiving this for free, we sell it for $195 retail. But if you're interested in receiving it for free, send me a note, and we should have this pretty much up and going by March of next year. We're just going through beta testing now. We sent it out to several people, and they're, if you will, sort of, analyzing it, tearing it apart, making sure there's no wacky solutions. Sensitivity analysis, of course, is critical to this kind of testing. So we're doing that now. But if you're interested, we certainly would be pleased to send you the passwords and so forth to get a free copy. So we have these resources. I do want to say this. I'm very interested in doing hybrid full-scale structural testing of pervious concrete with permeable interlocking concrete pavements. Pervious concrete, of course, is maybe 2 to 3 times stiffer than just the open graded material, just on a layer coefficient basis. And so you can get probably 2.5, 3 times more easels than with just unstabilized layer, maybe more, maybe less, depending on thickness of the pervious concrete. I think the benefit of the pavers, is the freeze-thaw durability, de-icer durability in the winter. Pervious concrete is a bit the Achilles heel. But the blessing of pervious concrete, of course, is its stiffness. And so we are seeing a few contractors actually doing this in the north, actually combining pervious concrete with PICP, with the pavers themselves on low-risk areas, parking lots and so forth. So it's interesting that people are already doing this, and would like to do some full-scale testing so we can up the structural capacity, the easel capacity of these pavements, so they can be used more extensively in stormwater management, in flood control, to create a more resilient pavement. So
thank you, David. And David, are there any questions out there for the group? Bob, is there any online? Do you guys have any questions? I guess related to you're talking about using paver blocks above a pervious pavement. Does your designs right now allow for that? Ones that you have available?
No, they're just the design tables are just based on unstabilized open graded aggregates.
Okay.
But you can make, I think, some reasonable assumptions about the stiffness of the pervious concrete. But again, there's nothing like full-scale validation. That's one thing I learned from Dave Jones is the best way to understand a pavement is to break it. So
he's good at that.
yes, yes.
I guess the other question is in Minnesota, I guess I'm looking at the room here. I know some city streets like Duluth, other places have installed pavers. I don't know if they're quote pervious, but what designs do we go through for our cities for this? I guess David Smith, have you worked with any of the cities in Minnesota to install pervious paver systems?
Not really. I mean, keep in mind that there's two different interlocking concrete pavements. There's the kind that has sand in the joints and bedding, and then typically a dense graded base or a stabilized base. That is designed very similarly to flexible pavements. That is an impervious system, and then the permeable system is the one that was just explained here, with essentially open graded joint aggregate in the joints and the base and subbase to allow for storage and infiltration of stormwater runoff. So with regard to we call them regular interlocking concrete pavements, the ones that are impervious, we do use AASHTO 93 to design that, and there's actually an ASCE. I think it's 5816. There's actually a design standard for that, and we also have software on our website, which is pretty much straight out of that design standard to do the base thickness calculations for impervious pavements. So those tools exist. I think a lot of the projects that were built in municipalities in Minnesota and elsewhere didn't have the luxury of these design tools for regular interlocking and pervious interlocking concrete pavements, as well as permeable interlocking concrete pavements. I am aware of a couple of projects, in the Minnesota-St. Paul area, mostly parking lots. There are lots of pedestrian areas I can think of in downtown Minneapolis, but I can think of a couple of parking lots that are done in permeable interlocking concrete pavements. University of Minnesota, I think, has got a fairly large area, and there's some others. But I think, the designers now have, I think, a validated tool that they can use here for the permeable interlocking concrete pavements.
Okay, we got one more question related to snowplow damage from my dear boss, Glenn Engstrom. Anything to deal with snowplows real quickly, because we only have a couple minutes now.
Yeah, snowplows. We recommend not using a steel blade, using one of those either rubber or plastic edges. Steel blades tend to abrade all pavements, doesn't matter what the material is. We haven't seen problems with snowplow blades catching pavers and flipping them out. I've got videos of snowplows going over permeable pavements in the winter, with not much, no problem really, and just moving across. But the blades, we recommend softer blades, not because the pavement is necessarily will be damaged, but I think people just don't want their pavements scratched.
Okay. Yeah, I mean, those are beautiful pavements, real decorative. I know in Duluth it's kind of fun to see paver blocks instead of asphalt or concrete in some ways. It gives it a unique look for the city. But I guess we're out of time right now. I'd like to thank both our speakers. I'd like to thank Bob Flipcheck for putting the time in before we even got here to make sure this all ran good. And he also bought the donuts for those people in the room here. So thanks, Bob. Again, we're looking for any research pays off topics for the future. Also, news articles. I guess related to David Smith. I I guess we'd like to continue. We always kind of have spots at Min Road where we're looking for ideas. We do have a spot on our website. Maybe I'll give you a call and we'll talk a little bit about maybe getting a placeholder in there for a possible test section that people might consider that's helping kind of the future of Min Road. So
sounds good.
Thank you again for your talk, and thank you again for everyone's participation. And we will see you in February. We'll be skipping January because of TRV. Thank you.
Okay. Thank you, everyone.
Thank you.